my Calc 2 class today. I said, so in lieu of, if you can't attend the presentation, I'll give you a take-home quiz. And I think I made it too hard because none of them are here. And I think they're all working together on the take-home quiz. But anyways, what I want to do today is I want to present two proofs that I have on mathematical induction. They're very specific types of proofs. So we're going to spend quite a bit of time building up the machinery that we kind of need. This presentation is particularly geared toward the undergraduates, and I really appreciate, I see some former students here and some current students, and this presentation was really written with them in mind. There's a poster on the way out of the Ram's Den. It's a saying by Nelson Mandela, and it says that the most powerful weapon in the world is education. And the first time that I published, I remember my graduate advisor saying to me, "Karen, don't you feel powerful?" And it was, in fact, one of the most powerful feelings. When you have something to say that nobody else has said or nobody else has presented, it's really one of the most powerful feelings in the world. So anyways, without further ado, let me tell you a little bit about what we're going to talk about today. I'm going to introduce the process of mathematical induction, talk about what it is specifically so that you can recognize those steps in the proofs that I'm going to show. Something called the triangle inequality. Both of the proofs that I'm going to present to you today are very specific types of proofs of triangle inequalities using mathematical induction. And then I have two very specific published proofs that I want to kind of walk you through as we progress through the presentation. So let me start with a brief introduction to mathematical induction. Mathematical induction, so suppose I make a claim that I have a formula that generates prime numbers. And I tell you that when you plug the value 1 into this formula, it's going to generate a prime number. By the way, if I had that formula, I wouldn't be standing here. I'd be a very rich person. But let's just assume for sake of conversation, that I have this formula that generates prime numbers. And then when you plug in a value of 2, it generates a new and unique prime value, and so on and so on. And the question is, how can I prove to you that for every natural number you plug into my formula, it generates a new and unique prime number? Well, that's the power of induction. That's the type of proof that mathematical induction works best on. It's the type of proof that works when you're trying to say that a statement is true over a whole set of values. Usually those are the natural numbers, 1, 2, 3, 4, etc., or for an infinite sum of numbers. And my particular proofs are interested in sums. The common and most simplest form basically consists of 2 steps, and that's where we're going to start. I'm going to show a couple of examples where there's really just 2 steps to induction. You show that it holds for some initial condition. Usually that's when n is equal to 1. Like my prime formula number will generate a prime number when you plug in the value n is equal to 1. And then here's the key of induction. It says, if you can show that your formula works for some kth value down this imaginary row of values, somewhere down the middle, not the 3rd value, not the 4th, but the kth. And if the kth value can be used to show that the next value is true, then the inescapable conclusion is that it would be true for all of the values through that set of natural numbers. So we're going to start with a simpler claim that actually is true. I'm going to claim that when you add up the first n odd integers, the value that you're going to get is n squared. So for example, when n is equal to 1, the first odd natural number is 1, and in fact, the sum is equal to 1 squared. If you add the first 2 values, 1 plus 3, you'll notice the sum is actually 2 squared. The sum of the first 3 odd integers, 1 plus 3 plus 5, is in fact 3 squared. And it looks like this formula actually works to sum up the first odd natural numbers very well. But again, how can I prove to you that it works for the first 100 values or the first 500 values? That's the form of induction. So here's a general statement that says if I'm going to add up n of these values, the value in the nth position would take on the value of 2n minus 1. I actually want to show that this statement is true. If I sum up the first n odd integers, I want to show to you that I'm actually going to get a sum of n squared. That's my job. So on the next slide, what I'd like you to imagine is that these statements, when n is equal to 1, when n is equal to 2, when n is equal to 3, can be thought of as dominoes kind of lined up in a linear fashion. And the idea behind induction is, if you can show that the first statement is true, and when it's true, there come some of my calculus kids, they come in late just like they do a lecture. Isn't that terrible? I shouldn't have to put up with this stuff. So I want to embarrass them. I do that in class too. Here comes the real slackers. They're coming in real late. So when n is equal to 1, I'm going to imagine that that's my statement, that in fact the sum of the first odd integers is equal to 1 squared. The sum of the first 2 odd integers is equal to 2 squared, et cetera, et cetera, et cetera. And in my mind, I'm going to represent the fact that when I show it's true, it falls to the right, causing the next domino to actually be true, to fall to the right, causing the next domino to be true, causing that to fall, et cetera, et cetera, et cetera. The idea, the key, the nuance to mathematical induction is that eventually what you want to do is you want to say, well, if I can show that the kth plus 1 statement is true, using the fact that the kth value is true, again, the inescapable conclusion would be that all of these dominoes would cause each other to be true, and thus it's true over the entire set of naturals. That's the idea. So pictorially, that's kind of a good image to have. Not sure where. Okay, so we're actually going to do we're going to do a couple of mathematical examples here so that you can see the process. So here's my statement written again, and I have the sum of the first n odd natural numbers here, and my claim is that it's equal to n squared for any value of n greater than or equal to 1. And so I want to show that if, and this is the key, if it's true for the kth domino down the road, and if I can use that to knock over the kth plus 1 domino, which looks like this, then in fact it would be true for all of the values. So students always look at this process from a pretty procedural standpoint. They say, okay, so this is what Dr. Adams writes on the board. And then I know that the next thing I have to do is write the word if and literally just replace every n that I see with a k. Then she's going to like that because that's going to look good. And then all I've got to do with the algebra is to replace every k in that previous statement with a k plus 1 and make sure my algebra works out, and she's going to give me an A. And at its most fundamental level, that's pretty much the process. But the idea is that while you're showing this statement is true, that's your ultimate goal. The key is to show that that statement is true, you must use that this statement is true. Otherwise, the kth value is not causing the next value to be true. And they're isolated incidents. And if you have an isolated incident, you don't have that chain reaction in the domino effect. So it's really key that we write this down and somehow use this. So here's typically what the proof looks like when the students are done. Now, proof by induction is a little bit different than other proofs. Usually the first statement of a mathematical proof is, this is what you want to show. And if that's what you want to show me in math, that should be the first line you write down. And then you do a bunch of gymnastics in algebra, and you try not to create your own algebras because we don't like that in mathematics. And this is going to be the last statement on your paper. That's generally how math works. If this is what you want to show, you start here, then you use whatever tools in your toolbox, and you end here. So with induction, however, that's actually the second line. The first line is we show that it's true for an initial condition. And so the initial condition here is 1. And I want to show that my equation works when n is equal to 1. So I literally plug in a 1, and I get 2 times 1 minus 1, which in fact is indeed equal to 1 squared. So with induction, we have to have that initial condition be true. And then we start the proof like we would start any other mathematical proof. I write down exactly what it is that I'm supposed to show. Now here's the key. There's the basic step, there's the induction step, 2 steps. Notice that these first k terms, it's assumed that these first k terms are equal to k squared. It's assumed that that's true. So you must apply the induction hypothesis, I'm going to replace the 1 plus 3 plus 5 plus dot 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 plus 2k minus 1 with the induction hypothesis that that kth domino is in fact true, and it's going to fall. And when it falls, it had better cause the remaining lines to be equal to k plus 1 quantity squared. Otherwise, the induction process has failed, and your formula probably isn't going to work. That's what it means. So when I replace all of these first k values with k squared, cleaning up this kth position, just plugging in literally k plus 1 up here, that reduces to 2k plus 1. And this is a perfect square trinomial. Where's my algebra teachers out there in the audience? This is a perfect square trinomial which factors beautifully into k plus 1 quantity squared, which is exactly what I wanted to show. And we're done. I want to show you this process a couple more times. It looks exactly the same. In most of these elementary processes, it looks exactly the same. And I want to do that so that you recognize it in a more complicated proof a little bit later on. So let me do another induction example. There's an often told, not necessarily true story about a young man in elementary school who was misbehaving. I was one of those children, I know. And the teacher decided to keep him busy by asking him to add up the first 100 integers. Now you can imagine being in elementary school and you had to add, and of course this was before electricity, before running water. This was quite a while ago. And if the teacher asked you to add 1 plus 2 plus 3 plus 4 plus 5, dot, 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 all the way to 100, that's probably a task that would take you maybe even several days, and you would probably get it wrong. Well, this young man, in about the amount of time that I've been talking, came up very quickly with this sum, which was 5,050. Now, he didn't use this particular process here, but that young man was Gauss, and we all in mathematics recognize that Gauss wasn't your average, probably elementary student. But anyways, if you check, I have a, oops, my slide went down. If you check, in fact, if you plug in the first 50 numbers, and you put 50 here, and 51 here, and divide it by 2, that in fact is 5,050. So his sum was correct according to my claim up here. And now you guys can all go home and wow all your friends, because now you can add up like the first 100 integers very quickly in your head. You could add up the first 5,000. The first 5,000 or 5,000 times 5,001 divided by 2. You can go home and amaze everybody. But let me prove this claim is true first. So I'm going to claim that when I add integers together, 1 plus 2 plus 3, all the way up to n, that in fact the answer will be n plus 1 divided by 2. And again, my initial condition is I'm going to start at 1. So here's the statement that I write on the board for my students. I say, okay, I want you to prove this. And so they dutifully, again, it looks very procedural to them, they dutifully say, well, what I need to do is I need to use that the kth value will work, and then I need to show that going to the very next term, adding k plus 1, adding one more integer, is going to make this value get bigger by 1, and this value get bigger by 1. So, generally speaking, they can do that relatively procedurally, and this is where they start the proof, because that's where a mathematical proof starts. They start with that on the left. And you can see where they've copied that over here. Now I use my induction hypothesis right here, that the sum of the first k is equal to k plus 1 divided by 2. I add the next term value, which would be the k plus 1. I do a little algebra. I get another kind of, not a perfect square trinomial, but I can factor this k squared plus 3k plus 2, and I, in fact, algebraically get exactly the result that's there. And so mathematical induction at the undergraduate level, when we teach it in discrete math, takes on that pretty much that same flavor. We do a lot of equalities with them and get them kind of to understand the basic process of mathematical induction. So my two proofs are mathematical induction, but my two proofs use summation notation. So I want to do the exact same proof I just did, only instead of writing 1 plus 2 plus 3 plus 4 plus 5 dot 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 plus n, I want to introduce a shortcut way of doing that. Don't let sums scare you. A sum is just a big list of numbers. The I is called the dummy variable. It tells you where to start. Start at 1 and count up, sum up to n. So this represents, in shorthand notation, exactly what we had on the previous slide, 1 plus 2 plus 3 dot 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 plus n. And you can see that I have the same formula on the right that I want to end with. I'm going to have to use the fact that the sum of the first k integers is equal to k plus 1 divided by 2. And ultimately what I want to show, using this fact, is that when I add up the first k plus 1 integers, I end up with one more value of k in every spot. And so again, induction starts a little bit differently. You will always see a proof by induction. Authors won't tell you it's a proof by induction. They'll just give you the initial condition. And you know it's a proof by induction. When I plug in a 1 plus 1 divided by 2, I get, in fact, the sum is 1 and it works. And so now I'm gonna start my proof, and I'm gonna start with adding up all the way up to k plus 1. I pull out the kth domino. You're gonna see me do that. I have to pull out what I need to use, and what I need to use is I know what the sum of k is. The sum of the first k is k plus 1 divided by 2, so I substitute that in, and I get the exact same process I had on the previous page. So don't let sums scare you. Sums, that's just one of the pieces of machinery that we need to get to my proof. Sums are just a bunch of addition. Just think of it as a bunch of addition. Okay, so we need a few more tools in our tool bag. So I like this statement about inequalities. I found this statement when I was preparing this presentation, and I think it's appropriate. It happens that often in mathematics, the more freedom one has in creating a solution, the more difficult it is to solve the problem. Often the easiest problems to solve are those where there's really only one way to get a solution. In particular, this means that it is often more difficult to prove an inequality than an equality. So I'm bragging a little bit, because both of my proofs are inequalities. So I want to show you how absolutely creative I can be. And you do have to be creative. So I'm going to start off with a simple inequality, again, so that you can see the pieces of the proof by induction, so you'll recognize it in my pieces. So I want to prove that 6n plus 6 is always smaller than 2 to the n when you plug in an n of greater than 6. It doesn't necessarily work for n is equal to 5 or 4 or 3. But this inequality is true whenever n is greater than or equal to 6. So that's my new initial condition. And I want to show that if it works for the kth domino, and I can use that fact to show that it works for the kth plus 1 domino, then I'll know it's true for all of them. I have to absolutely use this fact in my proof by induction, or I haven't used the right process. So I start my process exactly like I do all mathematical statements. I'm going to show that it's true for my initial condition of 6. So when I plug a 6 in here, and I plug a 6 in here, I get a true statement, because 6 times 6 plus 6 is 42, and that's strictly less than 64. We can all see that, so that works. So I'm going to start with the left-hand side of my inequality, and I want to end with the right-hand side. Now, when I talk about being creative, I just want to start out and say, this is a linear expression, all of you little budding mathematicians out there. And I want to show that it's less than an exponential expression. And that's a little bit tough to deal with. I mean, how are you going to work a linear expression so that you can end up with an exponential expression? Okay, got to be creative. So I start with my linear expression here, and the first job is to make sure that somewhere in there I pull out a 6k plus 6, because that's got to be used. And so if I just distribute, you start feeling really good right there, right? It's like, easy peasy, I can get a 6k plus 6 out of that without breaking a sweat. This one's easy, Dr. Adams. Well, so you drag down this extra 6 that's hanging around. Now I'm going to use my induction hypothesis that 6k plus 6, and notice the inequality, is less than 2 to the k. So I have to change it to a more restrictive inequality, right? And then I drag this 6 down. And then I'm sitting there with this expression 2 to the k plus 6. And this is where I have to look ahead. I need to end up with a base 2 exponential expression. I can't have this constant hanging around there. So I have to be creative and come up with a way that I can make 6 change into an exponential expression that's going to work for me. And clearly, 6 is less than or equal to 2 to the k for k is greater than or equal to 6, right? Because 2 to the 6 was 64. So 6 is less than 64, so I'll use that substitution in again, because it's convenient, because 2 to the k plus 2 to the k reduces to 2 to the k plus 1, and I get what I need. So this little statement here is going to become big in the next couple of slides. You got to be creative. When you're using a proof by induction and you're using inequalities, you got to look toward the end. You got to look at where you need to go, and then you got to use the tool. I see some people smiling. It's like, yep, that's exactly right. Okay. So the particular inequality that I focused on is called the triangle inequality. And the triangle inequality is very understandable for most of us. The triangle inequality in the Cartesian coordinate system, in our like little two-space, you know, when you're drawing on your paper, basically says this: if you grab an arbitrary side of a triangle, any side, not the longest, not the smallest, not the medium one, doesn't have to be a right triangle, but you grab any arbitrary side, you can't build a triangle unless that's smaller than the sum of the other two, which is being kind of demonstrated down here. So for example, if one of the sides of my triangle was as long as my 2 index fingers, and the other side was this long, and the other side was this, I can't build a triangle. Do you agree? So any arbitrary side's got to be short enough so that I can build these two triangles. Now, we're going to look at the triangle inequality on steroids in an upcoming slide. But just remember, all it says is that at any arbitrary side, it says it right here, has to be less than the sum of the other two. That's it. That's all it says. Or you can't build a triangle. Okay, we're almost there. We just need a few more tools, and these are kind of nice. So when you talk about the length of a triangle leg, and that's what we're going to be looking at, my inequalities basically talk about lengths of triangle legs. I just wanted to familiarize you that in two-space, in college algebra, you learn that the length of a leg can be calculated by taking x squared plus y squared and then taking the square root. And I wanted to use that exponent of 1/2 because my proofs use exponents. But it basically just says the distance between 2 points, if you think of the distance between 2 points as the length of a leg of a triangle, you can calculate that by saying how long is this distance and squaring it, how long is this distance and squaring it, and then taking the square root. And that's exactly what I'm going to do in my proofs. It's going to look a little bit more menacing. A few properties of exponents. If the bases are the same and you're multiplying, you just add the exponents. If the bases are the same and you divide, you subtract the exponents. And we don't like negative exponents in math ever, so we make them positive exponents in the denominator or vice versa. Now, one of my proofs does talk about complex numbers. For those of you who have solved the quadratic equation, right, from my, most of you, you've been in my calc class, my pre-calc class, you know that you get x is equal to negative b plus or minus the square root of b squared minus 4ac. So you know that you might get 2 plus negative square roots of 3. Right? So I'm looking at my Calc 2 students, and that's just a complex number. And I'm going to denote complex numbers as z's, and they're conjugates. Oh, and we love conjugates, right? Because when you multiply conjugates, things fall away, and it simplifies. So we love the conjugates, so I'm going to denote a complex conjugate as c bar. Just a few little tools. Okay, so I think we're ready to go. Now, I just want to refresh your memory. There's a physicist by the name of Rutherford that said, all of physics is either trivial or impossible. It's impossible until you understand it, my job, and then it's trivial. So when the slides come up, don't let them scare you. I'm going to walk you through because it's just induction with a couple of sums over some legs of some triangles. That's really all it is. And both of mine are reproofs of something called the Minkowskis Inequality. Now, I want you to look at this. This is the length of a triangle leg. Think of this as the length of a triangle leg. And it's a bunch of things, not x squared, but y and y squared and square roots. It's a little bit bigger than that. It's a squared plus b squared plus c squared plus d squared. It's over n dimensions. We're not going to restrict it to just 2 space. We can think of 3 space or 4 space or 5. So I have n components in there. And I can define the length of that leg any way that I want. It doesn't have to just be x squared plus y squared and then take a square root. I can define it this way. I'm going to sum up the pieces first, and then, in essence, square them, and then, in essence, take a square root. But Minkowski says you don't even have to square them. You could cube them and take cube roots. You could fourth them and take fourth roots. But it's really just the triangle inequality on steroids. Can you kind of see that a little bit? Okay. So I picked this inequality, and I have 2 proofs by induction that I'm going to do. The first one restricts all of my values to only be real numbers, and I think it's a little bit easier for undergraduates to understand. The second one I'm going to allow myself to kind of float over complex values, and the induction is a little bit trickier, but I want you to figure out why that last one is kind of tricky. The first one should look fairly familiar. Okay, I'm going to walk you through that. So here's the two special proofs. So I just published this one last year, and I basically say I'm going to calculate the leg of my triangles using square roots, cubed roots, fourth roots, fifth roots. You see how I'm letting p become all kinds of values? And so that's what I'm going to use over induction. I'm going to start by showing it's true for 1 over 2, and then I'm going to say it's true for 1 over k, and use that to show it's true for 1 over k plus 1, just to kind of lead in of where I'm going. And so here's my triangle inequality. I say basically any arbitrary leg has to be smaller than the other two added together. But I want to show that mine works for 1 over 3, 1 over 4, 1 over 5, 1 over 6. Okay, I'm going to use induction. Okay, so here's the first step in my proof. I say, well, the initial condition was p is equal to 2. So can you see where I stuck the p's are equal to 2 up there? That was my initial condition. And it turns out that this is a special case of the Minkowskis inequality that we've already known is true. Somebody else proved that the hard way, so we're just going to leave that alone, right? So my initial condition is already true. So I've written this out for us so we can see. So what I need to use is the fact that my triangle inequality works for p inside the statement, and eventually show that it works for p plus 1. That's my next domino. In this particular paper, I didn't refer to the domino positions as k's. I referred to them as p's because it was a power. I just thought that that was easier for me to use. So this is what I want to show. So you should know exactly what the next line is going to say. The next line is going to start with this guy. Oh, my highlighter won't even highlight that big, awful-looking thing. And this is what the last line is going to say. And this is an inequality, so I'm going to be very creative between that step and that step. But here's the first step. Okay, everybody ready? That's a rhetorical question. You can't say no. All right, here we go. So here's my statement. I want to show that my triangle leg for the 1 over p plus 1 is going to work. And the first thing I need to do is I need to pull out what I know is true. The Pete's power, right? Isn't that a fun word to say? Pete's power? That is just, yeah, it's kind of fun. Anyway, so the Pete's power works, and I'm going to pull that out, and I'm going to use my law of exponents. If the bases are the same, imagine if I put this on an algebra exam. If the bases are the same and you're multiplying, you just add the exponents. So if I add this exponent and this exponent, it will in fact equal 1 over p plus 1. So I've just split this into two exponents that are going to work for me. This is the one that I need, because that's my induction hypothesis, and can you see it? It was less than this piece, there's the little leg by itself, plus the little leg by itself. Does everybody see the induction hypothesis there, right? That's where the inequality comes. And then this extra piece, I'm dragging it along, and this is where I've got to become creative. Eventually, I want this to end up to just be this guy to the 1 over p, and this guy to the 1 over p. So I'm going to do some algebra. I'm going to try to figure out what I need to do, but I've got the end in sight. So the first thing I'm going to do is, remember that little negative exponent we talked about? We don't like those? I put it in the denominator down here. Can you see it? And then I just distribute it. This piece to this piece. So I have this sum, this whole bunch of addition in the numerator, and this guy in the denominator. And I have this sum, this whole bunch of pieces in the numerator, and when I'm multiplying, this guy in the denominator. Now this is where I've got to get creative. I want to end up with one sum here that just has a to the 1 over p plus 1, and one sum here that just has 1 over p to the p, 1 over p plus 1. But my bases aren't the same, so I can't combine them. But I'm working over the set of reals. So if I remove b sub j in the denominator, I'm going to make this denominator smaller, which makes the overall fraction bigger, which maintains the inequality that I'm trying to show. And if I remove a sub j over here, I end up with the basis being the same just in terms of b sub j. I make this denominator smaller, which makes this fraction larger, and it maintains my inequality. So that's the next thing you're going to see on the next slide. I removed b sub j from there, and I removed h sub j from there, and I maintain the inequality. I can pick anything I want, just like that 6 I changed to a 2 to the k. I can pick anything I want as long as it maintains the inequality. These bases are the same. Remember that little slide that said if the bases are the same, then you subtract the exponents. It turns out that 1 over p, subtract 1 over the product, p and p plus 1, ends up being exactly what I've needed. And I'm done. So that's my first piece, and I just wanted you to see the pieces of induction in there. And once you see the pieces of induction and you understand, you know, the broad strokes of the proof, it doesn't look so menacing. It doesn't look so menacing. It's just basically a big triangle inequality. Okay, so now just when you felt it was safe to go into the water. Okay, so this is a little bit more complicated proof that I wrote about 10 years ago. And this is over this set of complex. But this one does something really, really different right at the start. And I see several of my mathematician colleagues in there, so you're not gonna be allowed to answer. But I want to see if some of the students can see what's so very, very, very different about this proof by induction. So here's what I want to show. And I just literally, instead of using k plus 1, I used n plus 1. And again, this is just like a triangle inequality. I'm defining a special way of finding the length, and I'm always going to make sure that it's a square root. I'm always taking a square root here. And then it's equal to this square root and this square root. So it looks a lot like what we do in 2-space, not too different, other than I'm not taking x squared plus y squared plus blah, blah, blah. And I have a whole bunch of components here. This is n space, okay? Complex numbers. So that's what I want to prove. So the first thing I expect to see is this on the left, and then this is going to be on the right when I'm finally done. And so I'm actually going to start with my initial condition. And I say for n is equal to 1, if I plug in n is equal to 1, it's merely a restatement again of Minkowskis inequality, which somebody else proved the hard way, and so I don't have to bother with it. So I'm going to start on the left-hand side with this, and then I'm going to progress. So here's my left-hand side, just as I progress, and what I want to do is I want to get two little sums on the right that both say something about n plus 1. Now, what is hugely different about that compared to the previous ones? Anybody see it? I've never seen this done, and this is very creative. I'm saying that because the president's here, my boss is here. This is really creative. No, but I truly have never seen this happen. In all the other slides, the first thing I did with n plus 1 is I pulled out n. Or when I was starting with k plus 1, I pulled out k. Because I had to use something that was true about k, right, to substitute it in. But this one, I don't pull out n. I pull out n minus 1. I go back to, oh, I have to wait for Reza. Reza didn't hear my clever comment, but that's okay.
I did.
Oh, good, you heard me. So I pull out 2 values. And quite frankly, it's because for about a year, I pulled out the nth term and tried to substitute that in, and these are square roots. And it just turned into the ugliest mess I'd ever seen in my life. And I really got stuck, and one of my colleagues said to me, well, you know, to get rid of square roots, you need more of them. Pull out 2 square roots. I thought, okay, so I pulled out 2 terms. This is the only proof by induction that I've seen that relates the n minus 1 term to the n plus 1 term. So I wanted to show this to you because you can be very creative. Now, and this one again is a little bit more difficult. So here's the n minus 1 terms. Here's the nth term, and here's the nth plus 1. I just snuck those little pieces out. I did from here to here. These are elementary properties of complex numbers. Remember I was talking about conjugates? Okay. So if you had a little bit of experience, here's another thing I did. Got some conjugates. Because what I'm trying to do is I'm trying to get 2 sums out of all of this. 2 sums that are going to work. Now the problem is when you multiply complex numbers together, these are basically FOILs, right? We're not supposed to say foils, we're supposed to say binomial expansions, but all you guys know them as foils. You get a whole bunch of junk in the middle. And that junk in the middle with complex numbers has a real component. And that was really a nasty piece for me. I thought, how can I get rid of that and put it back into a sum involving complex numbers? So that was really the tricky piece. This is the really tricky piece. So I found an inequality of convenience. And this is a true inequality that involves complex numbers. And basically, I took this true inequality of convenience that I found, and I noticed that if I multiplied it by 2 and took some square roots, I ended up with exactly the expression, let me slide up, that I wanted to get rid of in my algebra up here. So I'm going to substitute that in. You're going to see me substitute that in right at the end of that expression. Here's my original expression. Here's the nth term. Here's the nth plus 1, and then I substitute this in. Why did I substitute that in? Doesn't that look like a perfect square of square roots expanded? Remember I said when you multiply square roots together, you get that messy looking square root kind of thing hanging around in the middle, right? When you guys multiply square roots. So this looks like perfect squares with a square root of a mess, that's a technical term, stuck in the middle. So I thought, well, maybe this will form a perfect square because that's kind of what I needed. Let me go back up to the top. What I needed was some perfect squares. See that? I needed some perfect squares. So I need them, I want them, so I create them. I say, well, if I let alpha be equal to this kind of square root, and I let beta be equal to this square root, then that mess up above, 2 real times the square root, ends up being just 2 perfect little squares right here. And then I can use the induction hypothesis. This literally is the definition of a sub n plus a sub n plus 1. This literally is a definition of b sub n plus 1. I can use the induction hypothesis, slide them in there, and then these guys fit real nicely into the sums where they belong. And I get the result that I was looking for. But that's kind of a slick proof by induction because, again, it relates the n minus 1 to the nth plus 1 term, and it was a very unpredictable kind of result. But that's it. So, and we've completed the induction. So these are the two proofs by induction that I got interested in when I was in graduate school. When I was in graduate school, I was taking an analysis class, and we were looking at Minkowskis Inequality, and the instructor kind of flippantly, as a side thought, said, you know, I think that you could probably do some of these generalizations using induction, and that was basically all they needed to. I went away, it was like giving a dog a bone. I went away for months, and I kept bringing in pieces, and finally, these two have been published, and in fact, Dr. Martin and I have a third Minkowskis Inequality over the set of complex. It doesn't use induction, but it's in review right now, and so that publication should be coming out soon. So you never know where these little gems, those guys, you guys that in my Calc 2 class, when you kind of fade out and I'm kind of saying stuff that you don't want to, you shouldn't do that because there's all these little golden nuggets in there, you know. So anyways, thank you. It's been a pleasure. And can I answer any questions? Thank you. Yes.
I'm going to embarrass myself by saying I really didn't understand very much, but because I'm not a mathematician. How long, when you're talking about putting this together, this proof, I mean, is that months, hours, what? How?
This second proof took me about 6 months of picking away at it. And it was only because I felt with my mathematical training that it should work. And I kept picking out just the nth term, and it just got ugly. And you know that in math, even you guys that are in discrete math, if your proof is getting uglier and uglier, you're going the wrong way, right? You know, it's not going to work out. So this one took me probably between 4 or 6 months, and it's such a powerful feeling when you finally finish a proof like this. It just works out beautifully. You know it's right. It's a very powerful feeling. That one took a while. The one that I just published, my brother called me names after I told him this. he said, how long did that take? And I said, well, I hurt my neck last fall, and I was sitting on the couch. Those of you in my classes, I was wearing the heating pad. And I thought, you know what, I think I can generalize that. And I think I wrote it down in about 20 minutes. And I thought, why didn't I publish this before? This one just literally, but it's not very complicated. This one just really kind of fell out. So it depends. You know, a lot of problems in mathematics, we suspect, we know that it should work, but the tools elude you. It's not a direct path. You do have to be very creative. The wider the background that you have in math, the more tools you have. I have outstanding colleagues here at Shepherd, and Dr. Martin and Dr. Wojciech both reviewed both of these proofs at some point in time, and even made comments like, Karen, I don't think you can do that. And I said, but I want to. So it just depends. It really does. And I always tell my students, every mathematician struggles with math. It's just we enjoy the challenge. For other students, it's more toil than joy, but mathematicians do struggle. It's not that we suspect it's true and it gnaws at you until you can put it down on paper. Yes?
A long time ago, I was at university taking science classes.
Mm-hmm.
There were two types of mathematical programs. One was pure math and the other was applied math.
Mm-hmm.
Is it still the same today?
Well, I'm a Shepherd alumni, go Rams, and so I had got my degree in mathematics here at Shepherd, and I went through a pure mathematics program, so I do believe, this is just my personal opinion, that over the years there's been an abundance, it's just prolific, the applied mathematics fields out there, actuary sciences. Our data analytics program is a perfect example of that. And I think those programs provide some very specific training, and those jobs are out there waiting for those students, and those are excellent career choices. I don't know if I'd had the opportunity at the time to go into an applied program that I would have. I always enjoyed the abstract mathematics, just always really did. So, Jason?
So, thank you.
You're welcome.
I could not follow your paper, but I followed this talk very well. The explanation was fantastic. So I enjoyed this very much.
Thank you.
I'm worried about the n-1 step, because if your basis is 1, and you're saying for every n plus 1, all I need is n, but you reach back to 0. Is that a problem?
That's a good question. And the idea behind mathematical induction is it's not really a one-to-one correlation. It's not like, the idea behind mathematical induction is if you can use, you show that there's an initial condition. If you can use the initial condition to show that the next one is true, and then use the same process, whatever process you used, you use the second one to show that the third one is true. But it must be the same process. If you use the same process to show that the second one causes the third one to be true, if you use the same process for the third one to the fourth one, it would seem like I would have proved this for every other n, perhaps. I don't know. That's kind of an interesting question. I'll have to ponder that for a while. My immediate response is, well, I had some very, very smart people look at it and got published, so I'm thinking I'm good. But if I'm not going to tell you. That's a good question, because I'd never seen that before. But it does involve the nth term, so I think we're okay. Interesting. Yeah. Yes?
I'm not a mathematician, and I didn't really understand, which is fine. I have no complaints about that. But I have a sense that in the bigger world, there's a lot of use of mathematics that people don't really understand. People don't realize that mathematics are the basis for a lot
Right.
Cybersecurity, example, password,
Exactly.
I'm using simple examples that
Right.
I would understand. Is that, can you give us some examples of where
Sure.
mathematics is used?
Sure. I read somewhere that abstract mathematics, the type of mathematics that was here today, runs usually about 2 to 250 years ahead of society needs. And I don't know how accurate that is or how you would come up with that. But let me just give you a great example. There was a mathematician, an English mathematician by the name of George Boole, that came up with this really small group structure in algebra that used ones and zeros. And it was interesting, but you know, it had absolutely no application at the time. And that's the basis of all of our computer systems now. And I might misspeak, the computer science people in the audience could probably help me out. But that's something that was studied abstractly as a very small group structure. You know, the reals are this huge, they're not even a group, they're called a field. The real numbers have all these properties, there's all these things we can do with them. That's actually a very sophisticated collection of objects with very sophisticated operations that we can do. And George Boole comes out with this little tiny thing. There's 2 elements in there, a 0 and a 1. There's 2 operators, an and an or, and it was interesting, but it was more of an academic exercise at the time. Let's talk about, you know, abstract algebra groups and what they look like, and it turned out to be one of the most important, smallest groups that we now use on a daily basis. So, you know, it's hard to know where mathematics is or is not going to lead us, but it is the core. In my opinion, it is the field that proves or disproves whether or not things that we can do with pharmaceuticals are going to work. Things that we do modeling the Ebola virus are going to work. Things that we do modeling space travel are or are not going to work. It's the core tool that we resort to. Can you unequivocally tell me yes or no? So, and I think that's what drew me to the field. You know, we don't have the I before E except after C kind of stuff. Yep. If I've proven it's true, it's true. It's going to work for all n. You can keep plugging away and trying all those n values in there, but you won't come up with a counterexample. So that's the nice thing about mathematics. But abstract mathematics, you know, we're a rare breed, you know. Will anybody ever want to develop a geometry that uses my metric to measure the lengths, because that's not a traditional way to measure the length of a leg of a triangle? Will they have any need to really come up with an 8-space triangle inequality? Well, I don't know, but you know, we know some things about it. And it adds to the general flavor. Do we understand, you know, how we can use numbers in different spaces and under different applications? Because it's right or wrong. And you can misrepresent and present information that are catastrophic, like the O-ring failure and the 1985 Challenger disaster, based on mathematical data that was not analyzed correctly. So. All right, well, thank you.
Thank you.